Так, ну что, будем проверять. Кто-нибудь проверяет? Кто идет, нет? А? Ну отлично, все, тогда можно начинать. Okay, at the previous lecture we proved a useful continuity criterion. We proved a useful continuity criterion for a linear operator between locally convex spaces. And in the special case of linear functionals, this criterion looks as follows. So if we have a locally convex space X equipped with a directed defining family of seminorms P, then a linear functional f on x is continuous, even only if it is dominated, or rather its absolute value is dominated, by a suitable seminorm from this family, dominated up to a multiplicative constant. So there is P in our family, and there exists a positive constant such that this relation holds everywhere on X. And then we apply this criterion together with the Hahn-Banach theorem to the following fundamental result. If X is a locally convex space and X0 is a vector subspace of X, then for each continuous linear functional f on this subspace, 0, there is a continuous extension. There is a continuous linear functional f on x, which extends f0. So each continuous linear functional defined as a subspace can be extended to the whole space. And useful corollary, this was corollary 1 of the previous lecture. If X is a Hausdorff locally convex space, then continuous linear functionals separate the points. So for each non-zero element little x in our space, there is a continuous linear functional f such that f doesn't vanish at little x. So continuous linear functionals separate the points. Of course, the condition that X is Hausdorff is essential, because if we have a non-Hausdorff topological space, then continuous functions never separate the points. So this assumption is essential, and the assumption of local convexity is also essential. We essentially used it in the proof, and actually there are some rather canonical counterexamples of Hausdorff and metrizable locally convex spaces for which the dual space is 0, so that the only continuous linear functional is identically 0. But for locally convex spaces, this cannot happen. So we have many continuous linear functionals, and probably this is the main advantage of locally convex spaces within the class of all topological vector spaces. So today our first goal will be to slightly generalize this result. Before we can do it, let me say a few words about quotients of locally convex spaces. So we have the following proposition. Suppose that X is a locally convex space and X0 is a vector subspace of X. And let Q denote the quotient map of X onto the quotient of X modulo X0. So let's equip the quotient with the quotient topology. The quotient topology. So let's recall that this means that a subset of the quotient U, a subset U of the quotient is open if and only if its pre-image under Q is open in X. So this is the quotient topology. I claim that, first of all, the quotient of X modulo X0 becomes a locally convex space. This is a locally convex space. Second, the quotient topology can be described explicitly as follows. So let's take a directed defining family of seminorms, P, directed defining family of seminorms on X. So let's recall that directed means that for any two seminorms from P, there is another seminorm which dominates, if we have two seminorms, say P and Q in here, then we can always find another seminorm R which dominates both P and Q. So here is essential that P is directed. We have proved at the previous lecture that each defining family is equivalent to a directed defining family. And here it is convenient to take the directed defining family. So I claim that the topology, the quotient topology on the quotient is generated by the family of all quotient seminorms P little p hat, where little p runs over big P. So here p hat is just the quotient seminorm. P hat is the quotient seminorm of P. And part three, I claim that the quotient of X modulo X0 is Hausdorff, even only if X0 is closed in X. Well, the proof is a more or less straightforward exercise for you. Essentially, it is very similar to the proof of the respective result about normed spaces, which you already know about. So the locally convex case here is it's proved in about the same way as in the case of normed spaces. Okay, now by using this proposition, we can extend corollary 1 as follows. Corollary 2. Suppose that X is a locally convex space and X0 is a closed vector subspace. Closed vector subspace of X. I claim that for each element in X which doesn't belong to X0, there is a continuous linear functional f on X such that f vanishes at X0 but doesn't vanish at little x. So this corollary extends corollary 1 because if X0 is the 0 subspace, if X is Hausdorff, then 0 is closed. And so for each non-zero element, little x, we can find such a functional f that f of x is non-zero. So corollary 1 is a special case of corollary 2, but actually corollary 2 is easily reduced to corollary 1 in the following way. So we take the quotient, which is Hausdorff by the previous proposition. The quotient is a Hausdorff locally convex space. And we just apply corollary 1 to this quotient. So the canonical image of little x in the quotient is non-zero, because little x doesn't belong to x0. So corollary 1 implies that there exists a continuous linear function of g on the quotient such that g of q of x is not 0. And now to get f, we just take the composition of g and q. F, which is the composition of g and q, is what we're looking for. Is what we need. Okay. Well, now our next goal is to discuss the basics of duality theory for locally convex spaces. And the central notions of this theory are dual pairs, and weak topologies. Well, let's introduce some notions. As usual, we work over the field of real or complex numbers and denote this base field by K. And we give the following definition. A dual pair of vector spaces is, strictly speaking, this is not a pair, but is rather a triple, consisting of two vector spaces, x and y, and a bilinear form, which will be denoted by angle brackets. So x and y are vector spaces. Now the angle brackets denote bilinear form of their product, bilinear, which is non-degenerate in the following sense. Condition 1, for each non-zero element little x in x, there exists an element little y in y, such that xy, the bilinear form evaluated at x and y, is not 0. And condition 2 is absolutely symmetric. For each non-zero element y, there is an element little x in x, such that xy is not 0. So in some sense, these conditions mean that our form is non-degenerate. And this form will be called a pairing between x and y. A pairing between x and y. Let's introduce the following short notation. So from now on, when we speak of dual pairs, we will use the following notation. So instead of writing this triple, we just write x and y in angle brackets. This is our notation for dual pairs. Okay, let's now make some simple observations related to these notions, to this notion. First of all, it's immediate from the definition that the notion of a dual pair is completely symmetric. Namely, if we have a dual pair consisting of two vector spaces x and y, then y and x also form a dual pair. We define a pairing between y and x by the following obvious formula. So this notion is symmetric. The second observation, well, first of all, we'll need some special notation for the algebraic dual space. That is, for the space of all linear functionals. So let's denote the algebraic dual of X by X hash. So this is the space of all linear functionals on X. In linear algebra, we usually write X star, but in functional analysis it is not convenient because the star is normally used for the topological dual, for the space of all continuous linear functionals on a topological vector space. So I use this modified notation. So the second observation is that we have two injective linear maps. Here we cannot assume continuity because X is just a vector space. X is not equipped with any topology. So, so far we are in the framework of pure linear algebra. In a few minutes we will introduce a topology on X. But at this point X and Y are just vector spaces. So here we consider the space of all linear functionals on X. So I claim that we have two embeddings, two injective linear maps. The first one takes Y to the algebraic dual of X. And explicitly takes an element little y to the following linear function on X. And symmetrically we can embed X into the algebraic dual of Y by sending little x to the following linear function. And these two maps are injective. Injective linear maps. So their injectivity is equivalent to axioms 1 and 2 here. So we will adopt, from now on, for convenience, we adopt the following convention. Usually we will identify Y with a subspace in the dual of X and X with a subspace of the dual of Y. By means of these two canonical inclusions. Okay, let's now look at some examples of dual pairs. First of all, if you take any vector space, X, then X and the algebraic dual of X form a dual pair. And similarly, you can interchange them and we still have a dual pair. Here, conditions 1 and 2 are more or less automatic. And example 2, which is probably the most important for us, if X is a Hausdorff locally convex space, then X, together with the topological dual, the space of all continuous linear functionals on X, and symmetrically X star and X are dual pairs. Well, here one of the axioms is automatic. If we have a non-zero linear functional, then of course it is non-zero after evaluating any suitable element. But the opposite, the symmetric condition, is not automatic. It is actually it is our corollary 1. We have no more corollary 1. Corollary 1 was that if we have a non-zero element in a Hausdorff locally convex space, then we can always find a linear functional which doesn't vanish at this element. So because of this corollary 1, we see that both axioms 1 and 2 are satisfied. So this is dual pair and this is a dual pair. And actually, this is our main example. I'd like to stress that these two dual pairs are not special cases of each other in the general case. So the advantage of using the language of dual pairs, the main advantage, is the following. When we prove some theorem about arbitrary dual pairs, we automatically get two different corollaries. The first corollary is about this dual pair, and the second corollary is about this dual pair. And these two corollaries are not special cases of each other. This is the main reason why we use the language of dual pairs. One more simple observation. Observation 3. If we take a normed space, X, and consider the dual pair of X and X star, then we have two inclusions. The first one is the embedding of X into the algebraic dual of X star. This is the embedding from observation 2. And we also have the canonical embedding into the bidual, X double star, which is of course contained in the algebraic dual of X star. So the observation is that this diagram commutes. The diagram commutes. This is immediate from the definition of the canonical embedding. Okay, well, so far the notion of a dual pair is purely algebraic. At the very beginning, we have no topologies on X and Y. In fact, once we have a dual pair, we can introduce several useful locally convex topologies on X and Y. And indeed, there are several ways of doing this. We'll discuss only one way of topologizing X and Y, which is probably the most important one. So suppose that we start with a dual pair, X and Y, a dual pair of vector spaces, and we introduce the following notation. For each element little y in Y, we define a seminorm on X by the following formula. So the seminorm will be indexed by little y, and it is given by the following formula. So clearly this is a seminorm. And we give the following definition. The topology on X generated by the family of all such seminorms. So the family consists of all such seminorms where little y runs over big Y. This topology is called the weak topology of the dual pair. The weak topology of the dual pair XY. And this topology will be denoted by sigma of xy. This is the standard notation for the weak topology of a dual pair. So the this notation means that the first space here is a space which we are going to topologize, and the second space y is the space which is the index set for our family of seminorms. So we topologize X with the help of Y. There are two important special cases of this construction. Special cases. Suppose that X is a Hausdorff locally convex space. Then the weak topology of the dual pair X and X star, so this is the topology on X, will be denoted like this. And it is called the weak topology of X. So when we speak of the weak topology on a locally convex space, we always mean the weak topology with respect to the dual pair X and X star. And if we interchange X and X star here, so X star and X is also a dual pair, then the respective topology on X star is called the weak star topology, and will be denoted like this. The weak star topology on the dual. The reason why I put the star here is that if in a special case where X is a normed space, we know that in this case X star is also normed space, and we have two formally different weak topologies on the dual. The first one is this one, and the second one is the weak topology generated by the dual pair X star and X double star. And so in order to distinguish between them, we usually put the star here and call it the weak star topology. In fact, it's easy to see that both the weak topology and the weak star topology can be defined for any topological vector space. A little remark. This is not essential today, but this will be used at the next lecture. So the weak topology and the weak star topology can be defined for any topological vector space X, in spite of the fact that in the general case X and X star don't form a dual pair. This is not a dual pair in the general case. But the definition of the weak topology is essentially the same. So sometimes this is useful. Okay, now let's look at some simple properties of the weak topology. Well, again, some immediate observations. First of all, the weak topology of any dual pair is Hausdorff. The reason is that our pairing is non-degenerate. So if we take a non-zero element in X, we can always separate it from zero by an element in Y. And this implies that the respective seminorm, where is it? The respective seminorm is strictly positive on little x. But this condition means exactly that our space is Hausdorff. So for each non-zero element, there is a seminorm from the defining family, which is strictly positive on this element. And so this topology is always Hausdorff. The second observation is about convergence. If we have a sequence in X, say Xn, then this sequence converges to X in the weak topology, even only if it converges at each element of Y. For each little y in Y. Well, indeed, we know that a topology, a sequence in an arbitrary locally convex space converges if and only if it converges with respect to any seminorm from the defining family. So if we look at this defining family, we see that the convergence is equivalent to this condition. And this convergence is usually called the weak convergence. Weak convergence. In fact, there is a standard convention that whenever we equip a topological notion with the word weak, this always means that we consider this notion with respect to the weak topology. So the sequence converges weakly if it converges in the weak topology. For example, another example, a subset of X is weakly closed if it is closed for the weak topology, and so on. So the adjective weakly usually means that we consider some notion with respect to the weak topology. Well, one more simple observation, observation 3. Suppose that we have an arbitrary topological vector space X with topology 2. This is a topological vector space. So I claim that the weak topology is weaker than 2, than the original topology on X. So this observation explains why the weak topology is so called. It is weak because it is indeed weak. It is weaker than the original topology. Well, why is it so? This is more or less immediate from the definition. Because for any continuous linear functional f on x, and for each element little x and x, the following set, and for each positive epsilon, the following set UF epsilon of x, which consists of those elements y and x, for which f of y minus x is less than 0, less than epsilon. So this set is obviously open in 2 in the original topology. Because f is a continuous linear functional, f of y minus x is just f of y minus f of x. So this is the preimage of an open set, of an open disk of radius epsilon under a continuous map. So it is open. But on the other hand, sets of this form, all sets of this form, form the standard subbase for the weak topology. And such sets form a subbase for the weak topology. So we see that each set from the subbase of the weak topology is open in 2, and this implies that the weak topology is contained in 2. Well, and in fact, for many natural cases, this inclusion is proper. For example, if we take any infinite dimensional normed space, then the weak topology will be strictly weaker than the original topology. There are several exercises about this comparison of the weak topology and the original topology in our exercise sheet 3. Okay, let's now discuss continuous linear functionals. So again, suppose that we have a dual pair, x and y, a dual pair, and observe that if we take an arbitrary element on y, so we can consider this element as a functional on x. So I claim that this functional is weakly continuous. Is a continuous linear functional on x equipped with a weak topology. Why is it continuous? Well, indeed, if we apply y to x, so y of x is just another notation for the pairing of x and y. But this is nothing but the semi-norm indexed by y and applied to x. And we know that linear functional on a locally convex space is continuous, even only if its absolute value is bounded by a suitable semi-norm from our defining directed family. So here we see that this condition is satisfied, and so y is continuous. And so we conclude that y is contained in the topological dual of x equipped with the weak topology. I claim that actually these two spaces are the same. So each continuous linear functional, each weakly continuous linear functional on x comes from y. This is our proposition 1. We have the following equality. Well, we already know that this space is contained in this one. And to prove the opposite conclusion, it will be convenient to use the following algebraic lemma. Suppose that X is a vector space, just a vector space without any topology. And suppose that we have a finite family of linear functionals, f1, fn, and another functional little f on X. Then the following conditions are equivalent. Condition 1, the kernel of f contains the intersection of the kernels of fi from 1 to n. And condition 2, f belongs to the linear span of the functionals f1 to fn. Well, the proof of this lemma is a nice exercise in linear algebra. Actually, you already met this lemma at least once when you, in your calculus course, when you proved the theorem about Lagrange multipliers. Of course, there you consider it the finite dimensional case, but this lemma is true for any vector space, not necessarily finite dimensional. Now let's now apply this lemma to proposition 1. So we start with a continuous linear functional on X. Let f be a weakly continuous linear functional on X. Let's apply our general continuity criterion for a linear functional. So there exists a positive constant c, and there exist finitely many elements from y, say y1 to yn, such that the following inequality holds. And this holds for each element x in our space. So this is just our continuity criterion for a linear functional. But now the right-hand side, what is this? This is just the maximum of yi evaluated at x. Again, here we interpret y1 to yn as linear functionals on x. But this inequality obviously implies that the kernel of f contains the intersection of the kernels of the functionals y1 to yn. if all these numbers are 0, then this is also 0. So we have this inclusion. But now our lemma implies that f is a linear combination of the functionals y1 to yn. And this linear span is obviously contained in y. So f belongs to y. And this is exactly what we wanted to prove. Okay, let's now deduce some corollaries from proposition 1. Corollary 1 is just a special case, but an important special case, so let's formulate it explicitly. Suppose that X is a Hausdorff locally convex space. Then, if we equip X with a weak topology and take the dual, then the dual will be exactly the same as the dual for the original topology. So the weak topology is weaker, is usually weaker than the original topology, but the dual space is still the same. Second, if we consider the dual space X star and equip it with the weak star topology, and then take the dual, what we get is exactly X. I mean X up to canonical inclusion of X into the algebraic dual of X star. As usual, we identify X with a subspace in here. So strictly speaking, this equality 2 means that the image of this embedding consists precisely of those linear functionals on X star, which are weakly star continuous. So we can identify X with this, the dual of the dual, equipped with the weak star topology. And this is just a special case of proposition 1. We apply it first to the dual pair X and X star, and then to the dual pair X star and X. Corollary 2. Suppose now that X is a normed space. X is a normed space. So we know that the dual X star is also a normed space. And so we have three topologies on the dual. The usual norm topology, given by the usual norm on X star. The weak topology, which is well defined because X star is a topological vector space. And the weak star topology, because X star is the dual of X. So I claim that these three topologies are related as follows. The weak star topology is contained in the weak topology, and the weak topology is contained in the norm topology on X star. And the part 2, well, the natural question is, how about equality? For example, what does this equality means? And here's the answer. These topologies are the same if and only if X is reflexive. So we get a nice reflexivity criterion in terms of the weak topologies. X is reflexive if and only if the weak topology and the weak star topology on the dual are identical. Well, let's prove the first part. First of all, we already observed that the weak topology is contained in the norm topology. This is our observation 3. So we have to show that the weak star topology is contained in the weak topology. This is immediate from the following observation. If we consider the family of semi-norms on X star, which generates the weak star topology So this family is indexed by elements of X. So it generates the weak star topology. And if we consider the family of seminorms, which generates the weak topology, so these seminorms are indexed by elements in the bidual in X double star. So this topology, this family generates the weak topology of the dual. So we observe that we have the following inclusion. Because the seminorm corresponding to little x is the same as the seminorm corresponding to the image of x under the canonical embedding into the bidual. So here I is the canonical embedding. So if we evaluate these seminorms at little f, in both cases we get just f of x, the absolute value of f of x. So this family is contained in this one, and so this already implies that this topology is contained in this topology. And this completes the proof of this conclusion. Let's now prove part 2. First of all, it's clear that we have the right to left implication. This is immediate from the proof of part 1. If X is reflexive, then the canonical embedding is a bijection, and these two families of seminorms are identical. So they are identical, and so they generate the same topology. So these topologies are identical. And to prove the opposite implication, so we suppose now that the weak topology and the weak star topology are the same, we do the following. We take the bidual of X, and we observe that this is the dual of X star equipped with the weak topology. This is corollary 1 applied to X star. Now we replace the weak topology by the weak star topology, because by assumption they are the same. By assumption they are the same. And now we look again at corollary 1, but now on the second part of corollary 1, and we see that this is nothing but X. And so, up to canonical inclusion of X into the bidual, these spaces are the same. So X is reflexive. By the way, another natural question which comes to mind when we look at this chain. So, well, these topologies are the same if and only if X is reflexive. How about this inclusion? Well, the answer is given in our exercise sheet. This inclusion is an equality if and only if X is finite dimensional. So for infinite dimensional Lorentz spaces, the weak topology.
You're going to get the middle equality.
Which one? This one. By assumption. So we prove the left to right implication. So we assume that these two topologies are the same. This is just our assumption. And we deduce from it that X is reflexive. Okay, let's now discuss linear operators between dual pairs. Suppose we have two dual pairs, x1, y1, and x2, y2. two dual pairs. And we give the following definition. Linear operators T from x1 to x2 and S, which acts from y2 to y1. We say that T and S are dual to each other. If the following relation holds, the pairing of T of x and y is the same as the pairing of x and S of y for each x in x1 and for each y in y2. Well, again, clearly this definition is symmetric. So if S is dual to T, then T is dual to S. Well, first of all, let's observe that if we start with T, if we start with T, I don't claim that such an operator S always exists. At this point, let's observe that if S exists, then it is unique. So, a little observation. So, suppose that T is a linear operator from x1 to x2. And let's consider the algebraic dual. We denote it by T hash. It acts from the dual of x2 to the dual of x1 by the well-known formula. So this is the algebraic dual of T. So I claim that there exists an operator S from y2 to y1, which is dual to T, if and only if T hash takes y2 to y1. And if this is the case, so in this case, S is nothing but the restriction of the algebraic dual T hash to y2. Well, this is immediate from this formula. So what is this? This is y applied to T of x. But y applied to T of x is T hash of y applied to x. So we see that if S exists, then S of y is just T hash of y. So S is the restriction of T hash to y2. So in particular, we see that S and T uniquely determine each other. In particular, if there exists S from y2 to y1, which is dual to T, then it is unique. It is just a restriction of the algebraic dual to y2. Well, now let's prove a useful topological criterion for the existence of dual operator. Proposition 2. So again, we suppose that we have two dual pairs, x1, x2, and y1, y2, and a linear operator T from x1 to x2. Then the following conditions are equivalent. Condition 1, T is continuous for the weak topologies on x1 and x2. T is continuous for the weak topology on x1 and x2. Condition 2. T is dualizable in the sense that there exists an operator S from y2 to y1, which is dual to T. And condition 3, there exists a dual operator S from y2 to y1, dual to T, and moreover S is continuous for the weak topologies. And S is continuous for the weak topology sigma of y2, x2, and the weak topology on y1. So at the first glance, 3 is stronger than 2, but in fact they are equivalent. Well, first of all, let's prove that 1 and 2 are equivalent. What do we know about continuous linear operators between locally convex spaces? Let's recall from the previous lecture that if we have two arbitrary locally convex spaces, x1 and x2, so we take a defining family of seminorms here and here, so then a linear operator from x1 to x2 is continuous if and only if the composition of this operator with any seminorm on x2 from the fundamental family of seminorms on x2 is continuous. So in this special case, this criterion can be written as follows. Condition 1 means precisely that for each element y in y2, map, which takes little x to the respective seminorm evaluated at t of x, is continuous. So this is a special case of our general continuity criterion for a linear operator. Well, but let's now look at the right-hand side of this property. So what is this? This is, by definition, the pairing of tx and y, or nothing but, this is nothing but y applied to t of x. So for each y, this must be a continuous function on x. But y composed with t is a linear functional. And the absolute value of a linear functional is continuous if and only if the functional itself is continuous. Again, this follows from our continuity criterion. So equivalently, this means that for each little y in y2, y composed with t is continuous on x equipped with the weak topology. x1 equipped with the weak topology. But we already know what is the dual of the space. So the linear functional on the space is continuous if and only if it comes from y1. This was our proposition 1. So by proposition 1, this means exactly that for each y in y2, y composed with t belongs to y1. That is, this means that t hash takes y2 to y1. And we have already observed that this condition is equivalent to the existence of the dual operator. This happens if and only if t is dualizable. And so we conclude that conditions 1 and 2 are equivalent. Okay, now, well, first of all, it's clear that 3 implies 2. This is obvious. And to complete the proof, we show that 2 implies 3. So to show that 2 implies 3, we assume that there is an operator S which is dual to T, and we observe that then in this case T is dual to S. T is dual to S. So S is dualizable. But we have already proved that 1 and 2 are equivalent. An operator between spaces for a dual pair is dualizable if and only if it is weakly continuous. So because we have already proved that 1 and 2 are equivalent, we apply it to S, we apply this equivalence to S, and we get that S is continuous for the weak topologies. And that's it. So this completes the proof. Here's useful corollary. Actually, there will be only one corollary, just a corollary without number. Suppose that X and Y are Hausdorff locally convex spaces. And T is a linear operator from X to Y. And let's consider the following conditions on T. Condition 1, T is continuous. Condition 2, T is continuous for the weak topologies. Condition 3, T is dualizable in the sense that there exists an operator T star from the dual of Y to the dual of X, given by the following formula. And condition 4, T is dualizable. There exists a linear operator T star from Y star to X star. And moreover, this T star is continuous for the weak star topologies. This operator is continuous. So we consider the following 4 conditions on T. I claim that in the general case, 1 implies 2, and 2, 3, and 4 are equivalent. And that's all I can say in the general case. But in the special case where X and Y are norm spaces, if, moreover, X and Y are norm spaces, then all 4 conditions are equivalent. It will be more convenient to observe that Y always implies 3. This is clear, because, well, if T is continuous, then of course, for each continuous linear functional f on Y, f composed with T is continuous on X. So we get a map from Y star to X star. The equivalence between 2, 3, and 4 is a special case of proposition 2. we simply apply proposition 2 to the dual pairs x star and y star. And finally, to complete the proof, we assume that x and y are norm spaces. Suppose now that x and y are norm spaces. And we have to show that all these conditions are equivalent. Actually, it will be convenient to show that 3 implies 1. So we want to show that T is continuous. Since x and y are norm spaces, this means exactly that T is bounded. So we want to prove that the image of the closed unit ball in X under T is bounded in Y. And here we use the Banach-Steinhaus theorem. By the Banach-Steinhaus theorem, a subset of a norm space is bounded if and only if each continuous linear functional takes it to a bounded set. So by the Banach-Steinhaus theorem, this is equivalent to the following condition. For each bounded linear functional f on y, f applied to the set is bounded. So this is what we want to prove. But what is this? This is nothing but T star of f applied to B1. And by assumption, so we assume that condition 3 holds, by assumption T star of f is a continuous linear functional on x, or currently bounded linear functional. So this set is indeed bounded. This is indeed true, because T star of f is a bounded function. And this completes the proof. In fact, this corollary can be essentially generalized. So I recommend you to do the following exercise. In fact, conditions 1, 2, 3, and 4 are equivalent if, well, exercise A. They're equivalent if X is a norm space and Y is an arbitrary locally convex space. Y is any locally convex space. So Y is not necessarily norm space. This can be any locally convex space, and the equivalence still holds. And exercise B, which is slightly harder. Let me put a star here. These conditions are still equivalent if X is metrizable. X is metrizable, and Y is any locally convex space. However, in the general case, these conditions are not equivalent. And this is one of the exercises in our exercise sheet 3. We still have 5 minutes left. Well, probably let's stop here. So our next goal will be to discuss annihilators in the context of dual pairs. So we have already met annihilators and pre-annihilators in the context of normed spaces. So our next goal will be to extend these notions to the setting of dual pairs and relate them to the weak topologies. In particular, we will prove some new relations between operators and their duals. For example, so far we don't know what is the annihilator of the kernel of T. If T is a bounded linear operator set between normed spaces, what is the annihilator of the kernel? In the general case, we only know that the closure of the image of T star is contained in this annihilator. And if T has closed image, then these spaces are the same. But for arbitrary bounded linear operator, we still don't know anything about this space. So at the next lecture, we will prove that this is nothing but the weak star closure of the image of T star, which is in general strictly bigger than the norm closure. And also, the next lecture we will prove the so-called Banach-Haloglu theorem, which implies in particular that the closed unit ball of the dual of any norm space is weakly star compact. It is never compact for the norm topology. We know that the unit ball of an infinite dimensional normed space is never totally bounded, so it is never compact. But we will see that this unit ball is weakly star compact, which is quite useful. Okay, thank you.